Swayam Prabha. Digital India. Educated India.
So far we have talked about constitutive relations of piezoelectric materials and related items. We started with basic electrostatics and then we looked into the conservation laws, and from there we derived the constitutive relations of the piezoelectric materials, and we looked into various forms of the constitutive relations and their interrelations, and then we talked about the sensors and actuators in a simplified way. Today we will solve some numerical problems from these topics, and these problems will be from basic electrostatics and some problems where the constitutive relations of the piezoelectric materials will be used. Here is the first problem. It says three charges are located at the vertices of a right isosceles triangle as shown below. What is the magnitude and direction of the resultant electric field at the midpoint M of AC, given AB and AC are 5 centimeter. So, here these dimensions are 5 centimeter, and we have to find out the electric field here at the mid of AC, and that point is designated as M. Now, this is the midpoint. So, the distance from here from this M to A and M to C are same, and if we look at the electric field at M caused due to A, it is directed towards this direction, and if I look at the electric field at M caused due to C, it is directed towards just the opposite direction, and their values are same. So, they will cancel each other. So, the net result of C and A at M is 0. So, the only thing that would contribute is our charge at point B, and that would be directed towards this direction. So, if I join B and M, and if we extend it, that extended line is our direction of electric field. Now, this is an isosceles triangle. So, we have 45 degree angle here, and we have 45 degree angle here, because our ABC is a right angle. So, we can say that BM is equal to MA. So, our BM is equal to AM, which is equal to AC by 2, and AC can be found out from AB and AC, which is AB square plus BC square root over AB square plus BC square by 2, and that gives me root over 2 by 2 meter, or we can again write 0.05 by root over 2 meter. So, electric field E is equal to 1 by 4 pi epsilon 0 multiplied by QB, the charge at B, divided by RBM if I want to denote this as a vector, then we have to write RBM cube and multiplied by RBM as a vector, and that would give us four pi epsilon, as we know, 8.8542 multiplied by 10 to the power minus 12, 2 by 0.05 divided by root 2 cube, then multiplied by 0.05 divided by root 2, and we have to write the unit vectors. So, this line makes an angle 45 degree here and a line 45 degree here. So, the unit vectors are one by root 2 I plus 1 by root 2 j. Where I is our unit vector along this direction and j is our unit vector along this direction. Now, we can simplify this entire expression and find out our E as a electric field as a vector. Now, we will look into the next problem. The next problem says a point charge of 10 microcoulomb is placed at a distance of 20 centimeter from another identical point charge of 10 microcoulomb. A point charge of minus 2 microcoulomb is moved from a point A to B as shown in the figure. Calculate the change in potential energy of the system and interpret your result. Now, to do this, we need to designate some distances here. So, let's call this point as 1, 2 and 3, and the distance from point 1 to point 2 is R12 and point 2 is point 3 is R23 and point 1 to 3 is R13. When it is moved to this point, let us call it 2 prime. So, it is R12 prime, it is R23 prime, and this, since in the deformed system these 2 points does not move. So, R13 is also R13 prime. Now, we can find out the potential energy at the beginning as UI, we say initial potential energy, and that can be found as if I take one by 4 pi epsilon outside, then we have Q1 Q2 divided by R12 plus Q2 Q3 divided by R23 plus Q1 Q3 divided by R13. Now, Q1 is this charge, Q2 is this. So, Q2 is minus 2 microcoulomb, which was initially here, and then it moves here, and Q3 is 10 microcoulomb. Q1, as we said, 10 microcoulomb. R12 we know 5 centimeter, R23 is shown here 15 centimeter. So, R13 is 0.05 meter, R23 is 0.15 meter, and sorry, it is R12. R12 is 0.05 meter, R23 is 0.15 meter, and R13 is 0.2 meter. So, once we put all these values and epsilon 0, as we know, it is 8.8542 into 10 to the power minus 12 coulomb square by Newton meter square. So, once we put all these values in this expression, finally, our potential energy comes to be minus 0.3 joule. Now, we will find these same quantities in the deformed configuration. To do this, we write a similar expression U if f means final 1 by 4 pi epsilon 0, and then by R12 prime plus Q23 by R23 prime plus Q1 Q3 by this is R and Q1 Q3 by R13 prime. Now, R12 prime is, write here, R12 prime is multiplied by 2 meter, which gives us 0.05 meter. R23 prime is this. So, it is square of this plus square of this under root. Meter, and this gives a value of root over 10 meter, and R13 prime, as we know, it is 0.2 meter. Once we put all these values here, Q1, Q2, Q3 we already know, then UF comes to be 0.8172 joule. Now, UF minus UI, if we subtract UI from UF, the value comes to be 1.1172 joule. So, UF minus UI is a positive quantity, which means to move this charge from here to here, we need to do some work. So, this concludes the second problem. Now, let us go to another problem. how much work must be done to move a charge q2 is equal to 5 microcoulomb from B to a new location at point C. So, the charge is supposed to be moved from this point to this point, and how much work is to be done. Again we can follow the same approach, we can find out the potential energy here and we can find out the potential energy here, and we can take the difference, and that would tell us how much work is to be done. Now, here we can see that here is a negative charge here and this is attracting this positive charge. So, this charge would try to bring it towards this side. However, we want to bring it from here to here, which means we need to do some work. So, this at this position the potential energy higher, at this position the potential energy is lower, and if we subtract them we will get a positive quantity, and that is the amount of work we have to do to move this charge from here to here. So, this can be solved using the similar approach that we adopted for the last problem. A point charge of minus 2 microcoulomb is located at the center of a cube with sides L is equal to 5 centimeter. What is the net electric flux through the surface? Now, to solve this, our net electric flux is surface integral of electric field ds, and that gives us the net electric charge. Now, from the Gauss law, this can be written as Q, which means the total free charge divided by epsilon 0, because if I take this epsilon 0 here, that gives me the electrical displacement vector, and electrical displacement vector dotted with ds and integrated over surface is equal to the total free charge Q, that is the Gauss law. And let us assume that it is in the free space. So, permittivity is 1. So, we have epsilon 0, and this quantity Q we know, because we know there is one point charge which is minus 2 microcoulomb. So, Q is equal to minus 2 into 10 to the power minus 6, and epsilon 0 is 8.8542 multiplied by 10 to the power minus 2, and that gives me the flux, and it should come to be minus 226 multiplied by 10 to the power 3 Newton meter square per coulomb. A charged ball of mass m is equal to 0.265 kilogram and unknown charge q is hanging by a light thread from a ceiling. So, this is the charge ball. A fixed charge q is equal to 5 microcoulomb on an insulated stand is brought close to the unknown charge. So, this is brought close to this, and as a result the unknown charge hangs at an angle theta is equal to 38 degree to the vertical as shown in the diagram below. So, because of that this assumes this inclination, and it becomes the angle becomes 38 degree. The distance between the two charges is 22 centimeter. So, the distance between these two is 0.22 meter. We have to find q. So, this is q and this is capital Q. First of all, because of this charge has come closer. So, now q is positive, so small q should be negative, then only it will come closer to it. So, small q is a negative charge, and at this position we have to find out the force here. So, if I draw the free body diagram of this small q, it looks like this. So, it experiences tension due to T, it has its own weight, the one weight is mg, mass into acceleration due to gravity, and here I have a force F. Now, the force F, as we know, the magnitude of the force F is 4 pi epsilon 0 q by r square. Here we are concerned with the magnitude only. We all know all these values, epsilon 0 we know, and we know q r square r. T is not known to us, mass is given to us. So, mg is 0.265 kg multiplied by 9.81, that gives us the mass in Newton. Now, from this free body diagram, this angle is 38 degree. So, we can write T cosine theta minus mg is equal to 0 if I sum up all the forces along the vertical direction, and T sin theta minus by 4 pi epsilon 0 r square is equal to 0. Then from these two equations we can eliminate T and find out our charge magnitude q, and that comes to be 4 pi multiplied by 8.8542 multiplied by 10 to the power minus 12 into 0.22 square multiplied by 0.265 multiplied by 9.81 multiplied by 10 38 degree. Divided by 5 multiplied by 10 to the power minus 6. So, we can calculate it and find out the magnitude of the charge q, and we know that it is a negative charge. So, that gives me full information about this charge. Now, let us look into this problem. So, this says a piezoelectric sheet of length 0.0508 meter, which is the dimension along one axis, width 0.0254 meter, which is the dimension along two axis, and thickness 0.000254 meter, which is the dimension along three axis, is subjected to a force F along direction 1, and a voltage V is equal to 100 volts is applied to the electrode along direction 3. So, the piezoelectric patch would look like this. And as we have seen, we have direction 1, 2 and 3. If we call this as direction 1, if we call this as direction 2, and this as direction 3. Now, the dimensions are given along all the directions, and it has electrodes along direction 3 at this surface and at the opposite surface, and a voltage 100 volt is applied along that. So, we have to calculate the free strain and block force, and we have to find out the variation of the strain along direction 1 with the applied force. So, to find out the free strain, so here we find this equation useful, S11 E multiplied by sigma 1 plus D31 multiplied by the electric field E3. This can help us finding out the free strain as well as the block force. Now, electric field E3 can be related to the voltage V by, so it is V by Tc, where Tc is this dimension thickness of the piezoelectric patch, and this we can call Bc. Now, so Tc we know that the dimension is given 0.000254 meter. So, to find out the block free strain, it is not free strain means when the piezo is not constrained, it can expand freely. So, the stress is 0. So, in that condition the equation reduces to S11 is equal to just D31 V by Tc. D31 is given to us minus 274 multiplied by 10 to the power minus 12. Voltage is 100 volt given to us 100 volt, and the thickness is 0.000254, and this gives us the amount of strain that we get. So, the strain that we get is minus 107.87 into 10 to the power minus 6. Now, we have to calculate the block force. Block force means when the piezo is not allowed to expand or contract. In that case, the full stress or full force is developed. So, strain is 0. In the same equation, if I put strain is equal to 0, then the equation can be written as S11 electric E. Sigma 1 means the amount of force, the block force that is generated. So, we call it FBL divided by this area. So, it is BC by TC, and then we have plus D31 V by TC. Now, if we find out the block force from this expression, it gives us minus D31 V divided by S11 E multiplied by BC. So, if we put the values 274 multiplied by 10 to the power minus 12 multiplied by 100 volt multiplied by the dimension 0.0254, and then we have to divide by S11 electric field, which is given here 16.5 into 10 to the power minus 12, and after simplification the force comes to be 42.18 Newton. So, we know the free strain. So, this is our free strain. So, we can denote this as epsilon P. So, these are free strain, these are block force. With that we can draw a diagram of force versus strain. So, to do that, if we plot the strains along these directions. So, we have, or let us plot force along this direction and strain along this. So, this is strain. The free strain is a negative quantity. So, it should be here. It is my free strain, and the block force is here FBL. Actually, when we have the block force known and when we have the free strain known, as we saw before, we can, for this kind of actuators which is linear, we can fit a straight line to it. The straight line equation would look like this. In this case, if we follow the procedure that we saw previously while discussing actuator load line, if you follow that, this becomes our straight line for this case. Now, if we join these two, it becomes our straight line showing the variation of strain with the force. So, this is our free strain that we got, this is the block force that we got. So, with that this problem ends. Now, we should go to the next problem. Now, let us look into this problem. A piezoelectric sheet of length 0.0508 meter, the dimension along one axis, width 0.0254 meter, dimension along two axis, and thickness 0.000254 meter dimension along 3 axis is subjected to a force F along one direction. So, it is subjected to a force along this direction. Assume that an electronic circuit moves all the charges generated by the piezoelectric sheet to a capacitance C. So, there is a circuit, this circuit moves all the charges here. As a result, we can assume that the electric field is 0 for the sheet. So, the electric field across this is 0. Calculate the voltage V developed due to a force F is equal to 25 Newton for a capacitance C is equal to 100 nanofarad. So, the value of the force is given to us and the capacitance is given to us. We have to find out the voltage here and the property of the piezo is given to us. So, we can write the equation, the relevant part of the constitutive equation d31 multiplied by sigma 1 plus epsilon 33 sigma multiplied by E3. Now, E3 is 0, it is stated in the problem. Sigma is the stress. If I know the force, the stress is force by area. So, I have to divide this area. So, it becomes D31 force by BC into TC. Now, the charge, if we know the electrical displacement D3, the charge can be calculated as D3 multiplied by BC into LC, and that is equal to our capacitance multiplied by the voltage, capacitance of this. So, we can simplify this and write voltage is equal to D31 multiplied by F LC divided by C TC. So, now if we put the values minus 274 multiplied by minus 12 multiplied by 25, the force in Newton multiplied by 2 into 0.0254 . So, this is basically LC. So, LC is just this value, we can just write it 0.0508, then divided by C, the capacitance 100 multiplied by 10 to the power minus 9, and then this has to be multiplied by the thickness 0.000254, and that is equal to our voltage, that is minus 13.7 volts. So, you can find out the voltage in this fashion, and that completes this problem. So, with this problem we will end this lecture here. I will see you in the next lecture. Thank you.